within 25 years, human beings will fly out into space and land on the moon. We know this is true. Man will conquer space.
The Johns Hopkins Science Review, presented by the Johns Hopkins Institutions and WAAM in Baltimore. This is the Johns Hopkins University, famed for 76 years for its contributions to learning and scientific research. Here in the many laboratories, Hopkins scientists are probing into the secrets of science, which, when discovered, will be translated into benefits to be enjoyed by you, the people of America. Each week, we are privileged to look over the shoulders of today's scientists and catch a glimpse of their research. On this, our 178th showing of the Hopkins Science Review, we present the first episode in 3 programs, showing how man will conquer space. To introduce this program on space travel, here is Lynn Poole of Johns Hopkins.
I have an airplane ticket here in my hand, and this airplane ticket is for a round-trip flight from Baltimore to Los Angeles. Now, if I offered it to you, you wouldn't be amazed. You might be happy, but you wouldn't be amazed because those flights are usual every day. But I wonder what you'd say if I offered you this ticket. Now, this ticket is for a round-trip passage, a round-trip flight to the moon. Now, it's a first-class ticket, and if I actually offered it to you, you might tap your head and point at me. But if you did, you would be wrong, because such a ticket will be used one day. Because one day, man will fly from our Earth up through the atmosphere and out into space and will land on the moon. Haven't you ever daydreamed about such a trip? If you have, come with me in your imagination and imagine that you are on a rocket headed outward into space. What would you encounter out in those regions?
Your rocket will leave the ground with a tremendous roar, gaining greater speed as it rises higher and higher. Passengers will look back at the Earth as the rivers and flat plains grow dimmer and dimmer. They will peer down on our highest mountains, which will then appear to be nothing but tiny anthills on the face of the Earth. Still looking backward, the space-bound passengers will see the Earth as it grows smaller and smaller, as it begins to fade in the distance. But as the rocket ship hurtles through space, the passengers will look through the forward portholes, will peer through the strongly shielded windows on the sides, and realize for the first time how vast is this limitless area we call outer space. As they speed along, they will know that around them, millions of miles apart, are 9 major planets. Our Earth is one of these planets, all of which are cold and can be seen only because they reflect the powerful fiery light from the sun. Next comes Mercury, Venus, our Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and finally Pluto. Perhaps the passengers will catch sight of some of the few billions of meteors in constant motion in our solar system. They will see the stars, which, unlike planets, give off light. And stretching millions of miles beyond our solar system are other solar systems, known as galaxies, tremendous clusters of stars which take their place in the vast area of the total universe.
Well, it's a mighty big universe, isn't it? But before we can use this ticket and go out into space, we must force our way up through the Earth's atmosphere. Well, now, what is this atmosphere? How high does it go? how far does it extend? And how far have scientists gone in learning how they can push their way through that atmosphere? Well, now, let's leave our fantasy and let's come right down here on Earth. And let's talk with the scientists and find out what are the facts. What are the facts about spaceflight? Well, now, there are questions which must be answered and can be answered by someone well-versed in astrophysics. And one of the people that can answer those questions is the director of the Laboratory of Astrophysics and Physical Meteorology at the Johns Hopkins University, Dr. John Strong.
The Earth's atmosphere is very interesting, Mr. Poole, especially the upper air, which separates the region where we live and navigate from the vast emptiness of space. It is like this. This is a globe which represents the Earth, and this is a canopy of the upper atmosphere which protects us from the ultraviolet light and meteorites of outer space. The air in which we live and navigate is densest at the surface of the Earth, and it gets thinner and thinner as one goes higher and higher in the atmosphere. You are all familiar with the problems which this thinning of the atmosphere poses for mountain climbers and for aviation. When you travel by plane and take off from the ground and rise to 3,000 feet altitude, the air is thinner, but you are still comfortable and safe. At 5,000 feet altitude, you will notice the air is getting thinner unless the pressure in your cabin is regulated to remain the same as it was on the ground. At 10,000 feet, you must breathe supplementary oxygen to remain comfortable. At 20,000 feet, it is necessary to have supplementary oxygen to remain alive. Beyond this, both pressurization and oxygen are required. Without them, you could not live, even a short time. Let us consider the structure of the atmosphere as the astronomers and rocket scientists do. First comes the troposphere. This is the cloudy part of the atmosphere, and it extends up to about 10 miles height. It gets colder and thinner the higher one goes. Next comes the stratosphere. This extends to about 60 miles height. Although it gets thinner, it remains almost constantly cold the higher one goes. Finally comes the ionosphere. This layer, extending from 60 to 120 miles in height, gets its name from the fact that it contains electrically charged particles, or ions. These ions are useful to man since many radio stations could not transmit beyond the horizon of their antennas if these ions did not reflect or bounce the radio waves around the curved contour of the Earth's surface. Beyond the ionosphere, our atmosphere compares in thinness or emptiness to the best vacuum man can produce. Beyond the 120-mile boundary of the ionosphere, you are in the region called the exosphere, which extends outward to infinity. In the exosphere, where man will make his expeditions in space, he will have to be protected from harmful ultraviolet rays and meteorites. The oxygen and ozone in the protecting upper air filters out the most harmful short wavelength ultraviolet rays. Billions and billions of meteorites dart out of space each day in our atmosphere, but fortunately they do not bombard us at the bottom because when they enter the upper atmosphere, their swift motion creates a friction and causes them to be heated, ignited, and burned to harmless dust before they penetrate to the Earth's surface. Only the largest ones reach the surface, and this only occurs rarely. Thus, if it were not for the protecting canopy of the upper air, the unfiltered ultraviolet rays and the falling unimpeded meteorites would destroy every living thing on Earth.
But now, so far, we have seen something of this great, this vast universe of ours, have seen the layers of the atmosphere through which we must push our way to reach space. And we realize that we must protect ourselves out there against the flying meteorites, against the ultraviolet rays, and many other things which might harm us. Well, now, we know that a vehicle can carry us out there one day, but before we can send men out there, there are certain problems which must be overcome. These are problems, these are hazards, which the scientists must overcome and must solve before we can go into space. Now, to discuss these problems and these hazards of life, we have brought for you from California a well-known astrophysicist who can answer many of these questions for us and tell us with what we must contend in space. He is from the Institute of Transportation and Traffic Engineering of the University of California, Dr. Heinz Haber.
You're correct, Mr. Poole, if you say that the engineering problem is only half of the story of conquest of space. There is also the human question. We must ask ourselves, will it be possible for man to survive in space? Will he be able to live if he is pitted against the utter void with no oxygen? There is no atmospheric pressure. There are all sorts of radiation, ultraviolet, cosmic radiation, and he will also be without weight. He will be floating without weight. Now, among those problems, the oxygen problems has been with us for quite a while. And we are happy to have tonight one of the newest developments, and this development will be shown to you by Dr. James Kennedy, who brought it down from right field where the suit has been devised and constructed.
Thank you, Dr. Haber. This is the Air Force T-1 altitude suit. It is the result of 6 years of research and development by the personnel of the Aeromedical Laboratory at Wright Field. This suit has been designed specifically to protect man against the hazards of exposure to extreme altitude. At 50,000 feet, unless man breathes oxygen under increased pressure, he will not survive. Above 63,000 feet, the fluids in the human body will boil at body temperature, and this will cause gaseous locking of the circulatory system and death within a few minutes. This suit is not an experimental garment. It is a production type suit and is being worn by about 150 people, Air Force and civilians. It has been worn on every high-altitude flight of the X-1 rocket research aircraft, and on one flight, this aircraft was well above 50,000 feet, and its cabin pressure was lost. The suit inflated automatically, delivering the oxygen from the emergency oxygen cylinder to the mask and to the suit, preserving the man's life and allowing him to live. I'll now have the Sergeant Lichty inflate the suit so you can see how it looks at altitude in the event cabin pressurization is lost. You'll notice moisture. Ordinarily, we prevent that by heating the face piece. Mr. Bill Bridgman wore this when he flew the skyrocket to 79,000 feet. This man is not as nimble as a ballet dancer, but he can do his job if necessary.
Such a suit would come in mighty handy in case, in a flight in the upper strata of the atmosphere or eventually in space, one of those meteorites would come along. This piece, cosmic matter, at one time has traveled about 40 miles per second, and he might have punctured, and it could puncture the hull of a ship easily, and then an explosive decompression would result, against which such a suit would be a very effective protective measure. Now, besides the oxygen problem, we have spoken of radiation. Now, there are essentially two kinds of radiation that might be harmful to man. One of those you have experienced yourself on the beach when you got yourself a bad case of sunburn. The sun emits ultraviolet radiation, and I have here a source, a flashlight of ultraviolet light, which I should like to show to you. We can't see this type of light. However, it can be made visible by a fluorescent screen similar to the ones you have on your television screen. Now we have to put out the light in order to make this visible. I point this source against the screen, and you can see that the screen is bright. Now let's try this piece of paper. If I interpose this between the source and the screen grows dark. This shows that even such a flimsy medium as this sheet of paper is able to stop these rays. Now similar devices would have to be used later in front of the windows, the portholes of a ship. A simple piece of plastic also stops these rays, and it's a good way of stopping these rays with these simple means. However, ultraviolet rays are not the only ones. We have also to deal with cosmic radiation. These are atomic nuclei that come from the depth of space, plunge into the atmosphere, and in their passage through the air, they produce all kinds of secondary rays. I can give you an example of how these rays act. I have here a Geiger counter. It's a type instrument that is used in atomic laboratories and civil defense. Every time a ray passes through this instrument, you hear a click in the loudspeaker. Now let us try the piece of paper, whether we can shield it off. You see it still goes on, so it doesn't work. How about this piece of steel, half-inch thick, which is pretty heavy? Let's show the Geiger counter below. Let's see what happens. You see the clicking still goes on. It shows that we cannot protect people against these radiations unless we use very heavy armor, such as 6 to 8 inches of aluminum, and of course such weights cannot be carried aloft. So we must ask ourselves, will there be any danger from these cosmic radiations? The answer is that we don't know. Not yet have we exposed experimental animals to this thin spray of cosmic radiation, and we are not yet prepared to pronounce space radiation safe. Now concerning the oxygen problem, it will become critical only in a case of an emergency. Concerning the radiation, man has no senses for their presence. So a man flying into the high altitude and eventually in space will, in the beginning, not find much difference between a normal high altitude flight or an actual space flight. There will be one thing, however, that will remind him drastically that space flight differs from conventional aviation. He will, upon leaving the atmosphere, he will become weightless. And this will be a very strange experience at best. Space and weightlessness will become synonymous like desert and thirst or Arctic and cold. Can you imagine what it will be like to exist in a realm where there's no gravity, where there's no up and down? Man will literally be suspended on a universal flying trapeze, rising, falling, twisting and turning. Unless kept anchored to a chair or bunk, weightless man will helplessly float about the entire space of his confining cabin. Now, it is a matter of common knowledge that weightlessness is brought about in space, but equally common are the misconceptions, how this comes about. Some people believe that if we detach ourselves from the Earth far enough, finally we may reach a point where the gravity becomes negligible. Or it is argued, if this would represent the moon, there is a point in between the two bodies, about here, where the action of the two bodies pulling in opposite directions cancel. However, this is not the case. Weightlessness is brought about by lack of support. And you all have felt weightlessness, or at least reduced weight in an elevator. When it starts going down, the rope slacks, and then you are being deprived of a certain amount of support, and you get this strange hollow feeling in the pit of your stomach, which tells you that you are about to get weightless. Weightlessness is actually not an attribute of space. I want to show you a weightless bottle right here in the studio. I can do this simply by taking away the support from this bottle. Now if I do this, it falls down. Now I will make it differently. First, let us take the bottle and see how it looks like when it is weight. When there is weight. The water is about 800 times heavier than the air, and if I shake it and get some bubbles into the water, you see they come up immediately because the water is heavier than the air. Now, I do the same thing, but I'm going now to pitch the bottle way up into the air. I hope I won't drop it. And then you watch the bubbles that float about in the bottle because they're weightless, they will stay there. Let me do it again. Once again. You see, this is weightlessness right here in the studio. Now, if man will enter a spaceship, he will then be just like one of those bubbles. He will float about in space, and he will then be weightless, such as these bubbles right here in the bottle.
Things are floating in space because they have no support, no pull from gravity. So, like the water and air bubbles in the gallon jar, objects in space have no weight. At first, the experience may be such a shock that the spaceman may claw desperately as he tries to get hold of something. As his spaceship is in free flight, or as he floats outside a space station, he will have to overcome this psychological reaction of fear to this weightlessness in order to carry on his work. This means that psychology will play a part in space travel. It will be a problem to be overcome. Our actions are based on accustomed body coordination, based on lifelong experience with gravity. This coordination will fail us out in space. The first quick movement of a man rising from a chair will send him coasting off into space. But man's aerial antics are not the only floating objects to be considered. Tools, pencils, and even the paper on which he keeps scientific records will float around the cabin of the spaceship unless securely anchored. To overcome this, all metal instruments must be made of steel, or at least have a steel strip on the instrument. These can be held snugly in place when pressed against a magnetized panel, similar to the magnetic board which holds knives for the housewife in her kitchen.
Now all this may sound and look a little funny to you, but actually behind these things there are some questions we have to answer. We must assume that man will have some trouble in controlling his body movements under conditions of weightlessness. He may even become disoriented. But how about circulation? How about digestion? How about breathing? Will it be possible? Can, for instance, somebody eat upward, something like that? Now, for that purpose, we have here a young lady. She's standing on her head, and you see she drinks against the force of gravity. And this is possible because these functions, also such as circulation and respiration, are being powered by elastic forces, which do not require the help of gravity. These conditions and these functions do actually go on undisturbed was shown in some experiments made by high altitude research rockets. You see here a rocket rising, and animals, monkeys and mice, have been brought above by these research rockets, and just like the bottle which I tossed upward a minute before, the monkeys were weightless, however much longer, because the rocket is a better tosser than it can be better done than with this bottle. And these animals lived through, and this has shown that the normal physiological functions are not grossly disturbed by the lack of weight. Now we must ask ourselves, are we justified to do such research, spend money and time on these studies? After all, the next flight to the moon is in no way around the corner. It will take quite some time before the first man will fly through space or even land on an alien body. But many of these problems of high-altitude flight are similar to those in space flight. I have here in my hand a model of the Douglas skyrocket, which was flown to an altitude in excess of 70,000 feet. Now this craft, if I tell you that it was that high, actually was some sort of a spaceship. 70,000 feet gives not a good picture. Let us express it differently. At that altitude, 96% of the atmosphere were below the feet of the pilot and only 4% were above. At that height, he had all the problems of the oxygen. He had to wear the suit, and if he would have flown another 50% higher, he would have entered the realm of the cosmic radiation. And so the problems of space, the human problems, are gradually creeping in. And still we can say that we are flying through space with these rocket aircraft, although we can do it only for a few minutes.
As Dr. Haber has pointed out, one of the first problems, the first step toward reaching space, is satisfying ourselves that men can live out there in space. They must be protected against the meteors. They must be protected against the ultraviolet light, the cosmic rays. They must be provided with pressure suits so that they can live and live comfortably in this space. All of these men are working on the scientific facts. These are the facts about space travel. Now, of course, the next step is how are we going to construct a rocket that will reach out into space, out into atmosphere. And we believe that engineers will be capable of constructing a rocket that will penetrate our atmosphere and reach space.
Astronautical engineers tell us they can construct such a rocket. How will they build it? What will it look like? How will it be propelled? How fast must it travel to leave this Earth? We hope you will be with us next week when Dr. Francis Clauser of Johns Hopkins University and Dr. Martin Summerfield of Princeton University show us how astronautical engineers plan to build a spaceship, when they tell us step by step how this rocket will be catapulted out into space. Be with us for the second chapter of How Man Will Conquer Space. The Johns Hopkins Science Review is produced by Lynn Poole in association with Robert Fenwick and Warren Weitzman. Directed by Paul Kane. Associate Director Ed Serro. Art direction is by Barry Mansfield. Your narrator has been Joel Chaseman. Parts of this program have been mechanically reproduced. The Johns Hopkins Science Review originates in the studios of WAAM in Baltimore.
This is the DuMont Television Network.
Within 25 years, human beings will fly out into space and land on the moon. Man will conquer space.
The Johns Hopkins Science Review, presented by the Johns Hopkins University and WAAM in Baltimore. This is the Johns Hopkins University, famed for 76 years for its contributions to learning and scientific research. Here in the many laboratories, Hopkins scientists are probing into the secrets of science, which, when discovered, will be translated into benefits to be enjoyed by you, the people of America. Each week, we are privileged to look over the shoulders of today's scientists and catch a glimpse of their research. On this, our 178th showing of the Hopkins Science Review, we present the first episode in 3 programs showing how man will conquer space. To introduce this program on space travel, here is Lynn Poole of Johns Hopkins.
Greetings, ladies and gentlemen, and welcome to another Johns Hopkins Science Review. You know, everybody all over the country is talking about space and space travel, and I thought you might like to see this issue of Collier's magazine, which has an article about space travel, a trip to the moon, by one of our guests who will appear with us next week. I also would like to thank Collier's magazine for loaning us some of the models that we're going to show tonight. Now, those of you that were with us last week know that we went up through the 120 miles of our Earth's atmosphere and pierced outer space. We found out about this great, vast universe that was around us. We saw some of the dangers that might lurk out there for men who were going to travel in space. The cosmic rays, the ultraviolet rays, the meteors, the comets, the lack of oxygen. And we saw that man will experience a very strange thing, weightlessness. He will float about helpless in space. Well, now, the next step on our trip to the moon and the conquering of outer space is the problem of how we're going to get there. Well, of course, astronautical engineers all over the world are working on this problem. They know many facts. They know what rocket propulsion is. So let us find out just exactly how a rocket is propelled. And we have as our guest the chairman of the Department of Aeronautics at Johns Hopkins, Dr. Francis Clauser, to tell us this.
Mr. Poole has asked me to come down from our aerodynamics laboratory at Johns Hopkins to tell you a few of the interesting things that aeronautical engineers and scientists are doing to make space travel possible in the future. I think that the question asked most frequently about space travel is, how will you propel a ship out in space? What will it push against? There's nothing out there for it to push against. You see, the automobile obtains its propulsion from the wheels on the pavement. All that the automobile engineer has to do is to shift the gears automatically, get rid of the clutch, and everyone is happy. However, with the airplane, the problem of propulsion is a bit more difficult. You see, there's no street in the sky for wheels to push against. Instead, the airplane must use propellers, which create a strong jet of air back, and it is the reaction from this jet of air behind the propellers that gives the propulsion to the airplane. Recently, aeronautical engineers have developed jet engines which are replacing the older propeller engines. These engines, although they are much more powerful and much lighter and can propel airplanes much faster, work on the same basic principle of propulsion. We have prepared a simple drawing which shows what goes on inside of a jet engine. You see, air is sucked in the front, compressed, mixed with kerosene, burned, and shot out the back in a high-speed burning stream. It is the reaction of this high-speed jet out the back that gives the propulsion. Let me emphasize again, it is the reaction of this jet that gives the forward push. It is not that the jet is pushing on the air. To understand this, we must remind ourselves of Newton's third law, which says that to every action there is an equal and opposite reaction. Let us see how this works. Here is a picture of a boy and his wagon. In this case, the action is for the boy to jump in this direction. The reaction is for the wagon to be sent in this direction. Now, when the boy jumps like that, then the reaction sends the wagon backward. So much for the theory. Let's see what happens in practice. Here I have my son, John. Johnny, we want to show the people how Newton's third law works. Now, what I want you to do is to jump off the wagon, and if Newton is right, then the wagon should get a backward reaction. You ready? Okay. 1, 2, 3, jump. You see, the reaction sent the wagon backwards. Next, I want to demonstrate how this action and reaction can be used for propulsion. I have here a small cylinder of carbon dioxide used to charge the ordinary seltzer water bottles. It contains gas under high pressure inside, and there's a cap here which, when I puncture it, the gas will shoot out in a high-speed stream. That's our action, and the reaction will be for the cylinder to be sent in the other direction. Now, let's see how this can be used for propulsion. I'm going to put it in our little aeroplane here, like that, and then I'm going to puncture the cap. Now, a rocket works in exactly the same way. Here I have the ordinary 4th of July rocket. It contains powder inside, and when I ignite the fuse, the powder will burn and send a stream of flames out the back. This stream of flames is our action, and the reaction will be for the rocket to be sent in that direction. Now, we are going to fire a rocket so that you can see this happen. Let's watch while they ignite the 4th of July rocket. You see, the reaction comes from the burning powder gases being sent out behind. Now, Newton's law says that this will happen out in space just the same as it does down here on the Earth. And this is what we use as the basis for propelling rocket ships out in space. Our calculations show that the 4th of July rocket, such as this, is much too weak and too inefficient to be used for a ship that would carry men out beyond the limits of the Earth's atmosphere. Instead, we must have something much more powerful than that. Now, gasoline has much more energy in it than the powder in the rocket. Here I have a bottle of gasoline and an ordinary pipe cleaner. And you see, when I burn the gasoline, I get a rather vigorous flame. Now, here I have a stream of oxygen, and you will notice how much more intense the flame was when we had the oxygen on it. This is just the kind of a powerful reaction that we need to have a spaceship go out beyond the Earth's atmosphere. Now, we have a rocket right here in the studio to show you what happens when we put the gasoline and the oxygen into a combustion chamber and have them burning. You see, the flames are shooting out in an intense stream that has a great deal of power to it. How would we use this in a spaceship? We have prepared a simple drawing that shows how this would be arranged. First, we would have to have tanks of gas. First, a tank for the gasoline. Second, a tank for the oxygen. Pumps and pipes to carry them to the rocket motor, where they meet, burn, and are ejected out behind. This action is continuous with the fuel and oxidizer meeting, being ejected out behind. Engineers have developed rockets powerful enough to carry missiles up to altitudes of over 100 miles, where the air is so rare that there's a molecule here, a molecule there, and another molecule over here. These rockets have reached speeds of 4,000 to 5,000 miles per hour. Now, are these rockets capable of carrying man out into space? The answer is no, they are not. Does this mean that we are going to have to wait many generations to be able to travel out into space? Not at all. Engineers have developed what they call a multi-staging. To illustrate that, I have a dummy of a rocket. Supposing that this rocket were fired into space and a small rocket, auxiliary rocket, were carried in the nose, and when the first rocket had achieved its high speed, the second rocket is then fired on, doubling the speed of the first. In this way, with techniques now available, we can send a ship out into space.
This is the way the astronautical engineers tell us that we will reach outer space through these multi-stage rockets, and we will eventually arrive at and build a space station that will circle and circle and circle the Earth. But we must hold our curiosity for a moment about this space station because we have some questions to answer. Some of these questions concern speed, some fuel, and others the payload that we will carry. Now, to answer these questions, we are fortunate in having the professor of jet propulsion from Princeton University, Dr. Martin Summerfield.
Mr. Poole, these questions are indeed important. We must provide answers to them before our designer can begin to work. For the answers we provide determine in a large measure the kind of design he will achieve. Let's take them in order. How fast will this rocket fly? Now, it is well known that it takes a speed of 7 miles per second for a body to depart completely from the Earth's gravitational pull and escape completely from the Earth. Now, when a space rocket is given this speed by the action of its propulsion system, climbing first slowly through the atmosphere and then reaching its high speed outside of the atmosphere, it will be able to go away from the Earth and be capable of remaining out there indefinitely, never to return. Or, if we wish, we can steer this ship so as to land either upon the moon or upon some nearby planet. Now, 7 miles per second is indeed a high speed. In more usual terms, let's put it in miles per hour. 7 times 60, 420 miles per minute. Times 60 minutes in an hour gives us 25,200 miles per hour. Now, 25,000 miles per hour is indeed a high speed. An alternative project suggests itself as at least the first step in conquering space. As Mr. Poole suggested, we might place a body in an orbit, circulating around the world. In this orbit, the body will behave as a stone at the end of a string. The Earth's gravitational pull substituting for the tension of the string, and the centrifugal force holding the body in its path. No additional propulsion energy will be required to maintain this body in its world-girdling flight, and so it will turn around in its flight once every 2 hours. Now, it takes a high speed, of course, to place the body in this circulating orbit. It has been calculated that a speed of 16,000 miles per hour, less than the 25,000 miles per hour, would be sufficient to bring this body with sufficient energy to continue indefinitely in its circular path. Let us assume that this is the answer we give our designer. As to the speed, 16,000 miles per hour. The next question he raised, what propellants shall we use in our space rocket? Now, in the past 30 years, a good deal of research has been carried out on fuels and oxidizers that might be used in liquid rocket engines. I have here 2 fuels that we might consider. The first, gasoline. Gasoline is a rather ordinary fuel. We're familiar with its properties. And indeed, it could be used in a rocket engine. Now, Gasoline, however, is not the most energetic of fuels. There are other compounds that might provide higher energy and consequently be more effective for our purpose. Among these more effective compounds, I have here one, hydrazine. Hydrazine, you can see, is a liquid and looks like water, but a good deal more hazardous to handle. I wouldn't want it to spill on my skin, and I would keep it away from ordinary equipment. Now, hydrazine provides greater energy than gasoline, but, of course, because of its hazardous nature, special equipment is required in its handling and loading the rocket. There are more energetic fuels than hydrazine, but these offer even greater hazards, or in some cases are more expensive, or in other cases are more difficult to manufacture. And so, among the large number of compounds that might be chosen, hydrazine stands out as at least one of the contenders as a fuel for a space rocket. Now, what about oxidizers? Here we have two oxidizers. The first, liquid oxygen. Now, liquid oxygen, of course, is the most natural one we would think of because it is oxygen in the air that supports combustion. Of course, we couldn't carry gaseous oxygen because the tank required to be too large. And so, in liquid form, we have a more convenient form of the oxidizer. But notice this property of liquid oxygen. I pour it into a tin can representative of the tank that might be loaded. It boils away rather vigorously. This limitation of liquid oxygen has suggested to chemists and chemical engineers to search for alternative oxidizers. One such alternative is nitric acid. Nitric acid does not boil away, but of course it is highly corrosive. And so again, we require special equipment to transport and to load nitric acid into the tanks of our rocket. But with such special equipment, taking care to keep it away from skin, from equipment, and from instruments, we can successfully use this oxidizer. Now, let us consider this combination for a moment. Hydrazine as a fuel, nitric acid as an oxidizer. This combination offers an interesting property. I can illustrate this property by the simple experiment that I'm going to perform here. Here I have, in a beaker, a small quantity of hydrazine. Here I have below it, in a crucible, a small quantity of nitric acid. I'm going to tip the beaker remotely so as to allow the hydrazine to pour into the nitric acid. Now watch closely what will happen. This is the property I wanted to illustrate. Spontaneous flame upon contact. Now, this property of igniting spontaneously is a most useful one because it assures the maintenance of steady combustion, continuous combustion, in our rocket motor. There is no danger now of the rocket flame blowing out, and therefore, more reliable operation is assured. Now, although this is a most useful and quite practical propellant combination, there are others that might be used. Rocket engineers have suggested a number of other practical possibilities. However, for the balance of our discussion, let us assume that this combination is the one for our space rocket. The next question our designer asked, what payload shall our rocket carry? We must answer this so that he knows what weight and what space he shall provide. Of course, the first flights out into space will undoubtedly be instrumented, pilotless rocket ships. These will be for the purpose of gathering experience in such flights and also for the purpose of gathering physical data from the high reaches of the upper atmosphere and from the regions out in space. But eventually, as we gather experience and as we know more about the characteristics of the atmosphere and of space, the first flight piloted will be attempted. And then, when we have this information, we will be able to tell our designer just what provisions he shall make for crew and cargo. Well, these were the three questions he raised. There are others, of course, that will come up in the course of the design. But bear in mind that today we know several propellant combinations that might be used successfully in the propulsion system of a space rocket. We also know the principles upon which we can base the design of at least the rocket motors of our space rocket. In recent years, several designs have been put forth by rocket engineers of ships that might reach into the outer space. Dr. von Braun, who will speak to you next week on this program, has proposed a three-stage rocket. I have here a model of it. The lower stage the middle stage, and the last stage. The last stage carrying in its nose the cabin containing the crew and equipment. Let us consider this rocket for a moment. Here I have a drawing of it. This drawing is placed alongside of a one-family dwelling to illustrate its towering size. It stands 300 feet high. It measures 65 feet across in the diameter at the base. It weighs 14 million pounds when loaded with hydrazine and nitric acid. And at the start of its takeoff, it delivers a thrust of 10,000 tons. 10,000 tons is a force sufficient to raise a medium-sized passenger-carrying ocean liner right out of the water. Now let's examine the interior of this rocket. I'll remove the outer skin to show it. Here we have the lower stage. Here we have the middle stage, and then the upper stage. In this upper stage is the cabin. The rocket motors here deliver the starting thrust. Here we have hydrazine, here we have nitric acid. Pipes lead the fuel and oxidizer respectively into the rocket motors. When the pilot flips the switch, the rocket motors start to fire, the ship rises from the ground and starts accelerating on its outward flight. Now, after a couple of minutes of operation, the lower stage has exhausted itself. It no longer serves a useful function. It is cast away. Propulsion is taken over by the middle stage. It delivers its thrust for a couple of minutes, and then it too has served its function, and it is cast away. The final stage, carrying the cabin containing crew and cargo to the final velocity of 16,000 miles per hour, takes over the job, and our propulsion period is complete. Now our spaceship can continue in its free coasting flight into the circling orbit around the Earth. Let's look for a moment at what our occupants are doing. Here we see the crew reclining in special couches. These couches are intended for support against the force arising from the high acceleration during the firing period. After the firing period, of course, they can leave their couches and move freely about in the cabin, carrying on their duties and taking scientific observations. This, Mr. Poole, is the general type of spaceship that might be used in the first piloted flight out into space. Of course, bear in mind that before this flight can be attempted, there will be many flights of pilotless, instrumented rockets for the purpose of gathering much more experience before we would attempt piloted flight.
Standing 24 stories high and weighing thousands and thousands of tons, it's very difficult for us to realize that such a giant can rise from a launching ramp, be forced up through our atmosphere and careen off into space. Yet we know that one day this will happen, when the engineers have designed the rocket, when they have decided on the exact propellants that they're going to use, when they have built this rocket, when they have put it in their launching ramp, and when men are standing about tensely waiting for the final word to launch this rocket into space, the world will be looking at them. The world will be wondering how this is going to come about. But when this day comes, around this rocket there will be technicians, there will be all sorts of people working on the preparations. When these have been completed, the first spaceship will be standing solidly, ready for its launching. And then the captain of this spaceship will be the last man to enter. He will enter his spaceship, and the doors will be sealed behind him. Everyone will grow tense, tenser, even tenser. And on the ground, men will watch, and then a very calm voice will start counting.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, fire!
The fiery and powerful gases from the first unit will rush from the tail of the rocket with a roar heard for miles. Slowly, awkwardly, the rocket will rise from the ground. Then, gathering momentum, it will force its way straight up from the ground with such increased acceleration that within 15 seconds it will have disappeared from sight, leaving only a vapor trail in the sky to mark its path. Rising to a height of more than 30 miles and traveling at a speed of more than 5,000 miles an hour, the automatic pilot will take command and tilt the rocket into its trajectory. Almost at the same instant, the fuel from the tail section, the first stage, will have been consumed. The tail section will be cast off and will parachute back to Earth. Traveling nearly 15,000 miles an hour, the center section will be dropped away, and the third stage will give the rocket its final thrust, which will send it hurtling along its orbital course. Now, in its orbit, the rocket will continue to fly around and around the Earth. Only man-made mechanical devices can ever stop the projectile as it hurtles through space. The rocket has entered the dark, vast area we call outer space, the extent of which, the limits of which, no one knows. It is speeding on its way to the space station. The Johns Hopkins Science Review is produced by Lynn Poole in association with Robert Fenwick and Warren Whiteman. Directed by Paul Kane, Associate Director Ed Serro. Art direction is by Barry Mansfield. Your narrator has been Joel Chaseman. Portions of this program have been mechanically reproduced. The Johns Hopkins Science Review originates in the studios of WAAM in Baltimore.
This is the DuMont Television Network.
The Johns Hopkins Science Review, presented by the Johns Hopkins Institutions and WAAM in Baltimore. This is the Johns Hopkins University, famed for 76 years for its contributions to learning and scientific research. Here in the many laboratories, Hopkins scientists are probing into the secrets of science, which, when discovered, will be translated into benefits to be enjoyed by you, the people of America. Each week, we are privileged to look over the shoulders of today's scientists and catch a glimpse of their research. On this, our 180th showing of the Hopkins Science Review, we present the third and last in 3 programs showing how man will conquer space. To introduce this program on space travel, here is Lynn Poole of Johns Hopkins.
During the last 2 weeks, many of you have written to us and asked us if we could suggest a number of things that you could read to follow your interest in space travel, and I would like to suggest to you this week's issue of Collier's magazine, in which you will find another article by our guest of this week to tell you more about traveling to the moon. And then some of you have asked about books. I think you might be interested in this book called Across the Space Frontier. In it, you will find many articles written by many of the guests who have appeared on the Johns Hopkins Science Review space programs. Well, now, you'll remember that 2 weeks ago, we demonstrated that human beings can live out into space when they are catapulted out there with a rocket. Now, if proper precautions are taken, if these men are equipped with pressurized suits, such as the man that you see here who is floating in the vacuum of space, you will probably also remember that these men must be protected against the meteors, the cosmic rays, the ultraviolet rays, and all the other dangers that one might find out in space. But then we next asked a question, what sort of rocket will take us out into space? And now, of course, the astronautical engineers described this kind of rocket, the 3-stage rocket that will start from the Earth and drop one stage, another stage, and then finally reach the outside. Now, this is the general type that we discussed. Now, the motors create a backward thrust, and out the rocket goes into space. But let's come back to Earth for a moment. How does this 3-stage rocket make its way out into space? Do you remember how we demonstrated this?
With a roar that is heard miles from the launching site, a cyclone of gas and fire will push from the tail of the rocket with such force that the reaction will push the rocket upward. Moving slowly for 1 second, the rocket will gather momentum, gain speed, and force its way upward with increasing velocity, until within a few seconds it will disappear from sight, leaving only a vapor trail to trace its path through the sky. Last week, we illustrated the way the three-stage rocket rises from the Earth and tilts into its trajectory. Gaining terrific speed, the fuel in the tail section will be burned and the section will be jettisoned, parachuting back to Earth. Then the central section will take over, being ejected in its turn. And finally, the third stage will push the rocket out into space. The rocket is now a man-made satellite, circling the Earth until some man-made mechanism brings it down or sends it out further into space.
Now, as you know from last week, this giant rocket that is circling around and around and around the Earth is carrying man and carrying materials to build a giant space station 1,075 miles above the Earth. Well, now, how will this space station be built? What will it look like? And what will its use be? Now, these are questions that can be answered by our guest of the evening, internationally known rocket engineer who is now technical director of the Guided Missiles Group at Redstone Arsenal. Our guest for this week, Dr. Werner von Braun.
As Mr. Poulos told you, we expect to build a giant satellite station 1,075 miles above the surface of the Earth. At that altitude, way beyond the atmosphere, the station will revolve around the Earth once in 2 hours. What will this station look like? Well, we might liken it to this gyroscope, the kind your children play with. Our space station will be a great circular wheel. The outer rim, right here, will be for the living and working areas for the space scientists and the crews. Then here in the center will be another area forming the hub, the space station. As you already know, everything is weightless in space. So the entire station will be in a constant spin so that the centrifugal acceleration in the rim will replace the missing gravity. The space station will rotate about its hub once in 22 seconds. The station looks like a tremendous inner tube, doesn't it? The actual space station will have to be built of some nylon reinforced plastic so that the station segments can be shipped to the outer orbit in a collapsed condition. Up in the orbit, the wheel-shaped station will be assembled from these sections and ultimately inflated like a tire. Of course, this inner tube affair you see here would not be strong enough to withstand the bombardment it will receive from tiny meteors, the size of a pea or less, which are pretty abundant in space. It also needs protection against the sandblasting it will take from the microscopic meteoric dust, which Dr. Strong told you about 2 weeks ago. If punctured by large or small meteors, the air pressure inside would rush out, create a vacuum, and crush the men inside the station. So our inner tube needs protection by an outer shell of sheet metal. Underneath this shell, we must have a space which separates the outer shell from the inner lining. This skin or outer shell is called the meteor bumper, taking the shock of meteors which evaporate upon impact. You remember that 3 weeks ago Dr. Haber said it was up to the astronautical engineers to protect men against meteors. Well, this bumper on rockets and satellite stations is a method by which we hope to protect the spacemen so that they may live safely in outer space. Astronomers tell us that we need not be afraid of the bigger meteors because they are few and far between in empty space, and chances are that we may stay there for 1,000 years in that outer orbit without a chance of ever being hit. But let's come back to our station again. Here we have portholes covered with glass, a type of glass which will filter the devastating ultraviolet rays and prevent them from entering the space station and harming the men inside. As the station spins slowly through space, it will be in constant contact with the Earth. So we will naturally need antenna, perhaps here at the top of the hub, to receive radio messages and television pictures from colleagues on Earth. Some men will work outside the station, and we must place safety hooks at the outside of the hub so they may fasten themselves to the station with safety lines. Remember, they are weightless and might float away. You may have wondered what these black patches are. They are the furnaces, the generators of the heating system for the station. Absorbing the heat of the sun, the blackened areas will transmit this heat inside. At the shaded side, the blackened areas serve as coolers, radiating excessive heat into outer space. A central circulation system will distribute the temperature-controlled air evenly throughout the station. This, then, is a quick view of the great satellite, which will be constructed out in space, over 1,000 miles beyond our Earth, placed there to study the universe and provide a launching site for the exploration of the universe, the planets, and the moon. Did you notice what I said just then? I said a space station constructed in outer space, over 1,000 miles beyond the Earth. If we're going to place it there, someone has to build it. But how? With the knowledge we have and with the rockets we will build, this building should not be too difficult.
A rocket of the type with which you are now familiar will leave the Earth, shoot its way up through the atmosphere and out into space at carefully calculated direction and speed. This three-stage rocket will carry men and materials with which to build part of the space station. When it reaches the 1075-mile orbit and starts around the Earth, the workmen, dressed in pressurized suits, will leave the rocket and take out the materials they have brought for construction. These pieces will be fitted together bit by bit with ease as they float, weightless, in space. When one crew has finished its celestial construction, it will climb aboard its rocket and return to Earth. A steady stream of space-bound and, alternately, Earth-bound supply ships will cause the space station to grow steadily larger. With one section completed, other rockets will arrive from Earth with more parts, other sections to be added to the slowly growing space station, until one day, the space station will be completed, rotating around its own axis as it circles the Earth. But let's see what the interior of the space station will look like. The bulbous, sausage-like object you see here is a space jeep, which will taxi new arrivals from the transport to the space station. When this space jeep approaches the space station, it noses into a strong, net-like berth. Here they will find storage rooms and equipment necessary to supply the men who will operate the space satellite. Down the corridor, one may well find an astronomical observatory, where scientists are studying the mysteries of the planets, nebulae, and the hundreds of other phenomena which we will never unravel until we can establish this station in space. Undoubtedly, there will be a Weather Bureau unit aboard the station, where meteorologists will study the weather over the entire Earth. Here on the upper level is such a Weather Bureau. From this height, the eyes of the space station scientists will sweep every inch of the entire surface of the Earth every 2 hours. They will learn much about weather and send back weather reports every 2 hours. Under this room, the visitor would find great television screens with pictures of what is going on down below, a vast panorama of everything happening on Earth as the space station passes in its orbit around our world.
We could take you further on an exploration, on a tour of this space station, through room after room filled with electronic equipment, laboratories that will be used by the men who are out there on this space station. We could wind our way up circular stairs because this space station will probably be built 3 stories high. But this will give you some conception of what a space station will be, how it will be built, and gives you a brief glimpse of it as an activity base in our celestial sky. Now, the thought of this fabulous space station almost defies our imagination, but it will be there. It will be built, shining like a new star out in outer space. Now, it will be the greatest laboratory ever built, from which men will study the other planets and learn a tremendous amount about this Earth on which we live. But it will be something else. It will be the base from which moonships will take off on their way to the moon, the second stage in man's conquest of space.
The space station provides us with a point of departure. The orbital speed of the station, 15,800 miles per hour, provides already the greatest portion of the speed required for a trip to the moon. At the same time, the moonship need not cope with the aerodynamical problems of flight through the atmosphere and therefore need not even streamlining. a matter of fact, the ship capable of flying from a satellite station to the moon will be a far cry from those sleek and beautiful streamlined rocket ships we all know from science fiction. It will be an ugly, functional design as the one you see here. Up here in this nacelle, a spherical, hollow container will live the crew. There will be the captain, the navigation room, living and dining quarters, and storage room, plus the entire guidance and navigation equipment. Down here are the propellant containers. There are 18 of them, with a total capacity of 800,000 gallons of hydrazine, which will be put into the upper tanks, and nitric acid in the lower tanks. These propellants will be fed into the rocket motors that you see here. There are 30 rocket motors. Some of them can be hinged to control the ship in flight. Others in the center are rigid. After these 5 days, our unpowered elliptical flight to the moon will intercept the moon's orbit. Now we have to turn the ship around and land on the moon tail first. Shortly before we reach the moon, we will pass the famous neutral point, the dividing line between the Earth's gravitational field and the moon's field, and from that point on, our fall towards the moon's surface will become faster and faster. At an altitude of 550 miles above the moon's surface, we have to turn the rocket motors on again for the retarding blast. And a little instrument which measures the altitude and at the same time our rate of descent will see to it and control the thrust in such a way that the rate of descent becomes 0 at the moment the altitude is 0. That means, in other words, that the ship will settle down on the moon like a helicopter. Once on the moon, we can shed these outer tanks too, and only the inner tanks of the ship are needed for the return flight to Earth. In one kind of our 3 ships, there will be no inner tanks, but they will be replaced by a cargo container. This ship is designed for the one-way flight only, and we will abandon this ship on the moon. The equivalent of the propellants of the round-trip ships in this ship will be payload, and in this way we are actually in a position to carry a very substantial amount of payload to the moon.
Up here on the space station, 1,075 miles above you, we are waiting for the arrival of more material with which to build the moon rockets. Rockets are arriving in our orbit and are pulling alongside of our space station because the rocket speed is the same as our space station. Workmen have been working for some time on constructing the moon ships. The ships have been built out in space much as the space station was constructed. The parts for the moon ship have reached us in predetermined order, so that workmen assemble the parts, putting them together like giant jigsaw puzzles. Let's look into the interior of one of these moon ships. Here in the interior of the ship, in the great globe at the top where the crew will live and work on their long trip, we see the special equipment and instruments they will need. The men will work in reclining positions, strapped to their positions so they will not float away from their instruments. Even at the dinner table, the men will be strapped to their seats. The food containers will move in tracks around the large circular dinner table so as not to float around the room. The crew members in their pressurized suits will go through an airlock before going out into space to work on the outside of the ship as it makes its long journey. Lines will hold them fast to the ship so that they will not float away in space. But now the moon ships are loaded, ready to take off from the space station. Everyone is tense. We are certain that you on Earth will view this historic takeoff because it is scientifically possible for television cameras here on the space station to transmit this event to you. The last-minute checkups are being made. Everyone is a bit nervous. And now, there, the flash you just saw was the ignition of the 90 rocket motors. Now here's the cargo ship as it takes off, moving slowly at first, then gaining speed as it leaves the space station until it is traveling at a rate of 19,500 miles an hour. After the first powerful thrusts of its rocket ends, it coasts on its own momentum. Empty fuel tanks are jettisoned and will float free and crash on the moon. Inside the ship, 3 flywheels are set in motion. These cause the ship to turn and fall toward the moon tail first. The rocket motors are turned on to act as a brake as the ship comes closer and closer to the surface of the moon. Now one of the ships is settling on the moon. The steel claws will be ejected from the sides of the ship as it lands gently. The first spaceship, the first human beings have landed on the moon.
Here you see the passenger ships, the exploration on the moon completed, taking off for the return trip from the moon to the space station's orbit.
Now, no matter how comfortable it may be on a space station or what may be found on the moon or how comfortable it is on the moon, no one wants to be left out there without a return ticket. A man who goes wants to be sure, very sure, that he will come back to Earth. How will this be accomplished? Well, if we know we can get out there, we certainly can get back, and Dr. Van Braun can tell us exactly how that will happen.
I will make you a quick sketch of the path to be followed by the rockets who returns from the space station's orbit. This here is the Earth, and this shady ring around the Earth is the atmosphere. Up here is our orbit, and our space station travels along at a rate of 15,800 miles per hour through the orbit. Now we take the upper stage of our space rocket around and retard that motion a little bit by giving it a rocket blast in this direction. We thereby retard the speed by 1,070 miles per hour, so that our ship is now slightly slower than the orbit. As a consequence, our ship will go into an elliptical path, which at this point here will cut into the atmosphere at an altitude of about 50 miles. At this moment, the ship will have entered the atmosphere nose first, and now the aerodynamical drag in the atmosphere will make itself felt. We now keep the ship in the atmosphere and retard the flight with aerodynamic drag. We make a complete glide half around the Earth, and at this point, almost directly underneath the point where we left the orbit, we will be down to sonic speed. Our altitude at this point will be 15 miles up. From this altitude, our ship can spiral down like a normal airliner and can finally land on the ground on a landing gear, and the landing speed will be no greater than 65 miles an hour.
Now, exploration of the outer reaches of this vast universe in which we live will bring new benefits. It'll bring new benefits for one reason, because scientists never forget that the ultimate results of their curiosity, of their brilliant research, of their investigation in laboratory on land and sea and into the universe is for one use only, and that is to make our lives a better life, a happier life, and we very much hope a more peaceful life. Now, those among us who bemoan the lack of new frontiers, who say that the pioneering spirit is past, who say that there are no new frontiers to conquer, these people are very wrong. Because as you have seen during the past 3 weeks, there are new frontiers, and the astronautical engineers and the astrophysicists are working and studying so that we may cross that frontier, a frontier that reaches hundreds and thousands of miles above us. Now, one day, perhaps in your lifetime, and I very much hope in mine, that some cumbersome man in pressurized spacesuits will walk very carefully and very slowly and enter a rocket, and this rocket will be catapulted up through our atmosphere out into space. And there in space, they will come alongside a spaceship, a space station, the type of station that we have shown you this week. And from that station, a moonship of the type that Dr. Van Braun has described will then take off and it will go to the moon. And we will one day be able to see the other side of that moon, the other face that man has never seen. And we'll photograph that side, and we'll see exactly what there is there. Now, why? Because we must probe the mysteries of the universe of upper atmosphere. We must also know a great deal more about our own Earth. And from this space station, 1,075 miles above the Earth, as you have seen by radar, by radio, and by television, scientists will use this space station as a laboratory, and they'll look down on the whole face of the Earth. Perhaps it will have a great deal to do with weather, to know what weather is. They can tell us what weather is coming. There'll be many more things that they can tell us when they build this space station. And speaking for myself, I, for one, believe they will do it. Well, now, after all this, what is there left to say but ask you one question? Do you remember that 3 weeks ago I showed you this ticket, this round-trip ticket to the moon? After having seen these 3 programs on space, what do you say now? Do you think we'll make it? Well, next week we're going to ask you a question that I'm sure a lot of you are wondering about. You've heard a lot about the so-called electronic brain. You've heard how it does mathematical problems at fantastic speed, how it can sit down and play chess with men. Well, how much of this is scientific fact? Next week, we'll ask the question and answer it. Can machines think?
In the last 6 years, machines have been invented that can solve difficult mathematical problems. And they are hard at work solving these problems for industry, government, and science. Some of these automatic computers, the so-called electronic brains, can do over 1,000 additions in a single second. Most computers have memories, and some can make choices. But does this mean that man has actually invented machines that can think for themselves? Next week, we are going to show you one of these high-speed electronic automatic computers. One of the men who invented them is going to show you how they work and what they can really do. Next week, you will see the scientists' answer to the question, can machines think? The Johns Hopkins Science Review is produced by Lynn Poole in association with Robert Fenwick and Warren Whiteman. Directed by Paul Kane. Assistant Director, Ed Sarrow. Art direction is by Barry Mansfield. Your narrator has been Joel Chaseman. Parts of this program were mechanically reproduced. The Johns Hopkins Science Review originates in the studios of WAAM.
This is the DuMont Television Network.